Welcome to the Tech Study channel. So, in the previous class, we have discussed about uh, 11th question and its answer. Um, and in this class, we will discuss about 12th question and its answer of Triple E subject, which is elements of electrical and electronics. So, the 12th question is basic techniques in JFET. So, first we will see what is JFET, what is transistor, then FET, then transistor, then working of JFET, and then passing techniques. And transistor. So transistor is a fundamental semiconductor device used to switch or amplify electronic signals and power. So switching means switching on and off, and amplifying means increasing the strength of the signal. And transistors are categorized by whether they are controlled by input current or input voltage. If they are controlled by input current, then they are called current control devices. Example, BJT, bipolar junction transistor. If they are controlled by voltage, input voltage, then they are called voltage control devices. Example, FET, field effect transistor. So what is FET means? FET is a field effect transistor is a voltage controlled terminal semiconductor used for switching and amplification. Okay, and JFET is a one type of FET. So we have seen BJT biasing techniques also. So in this video we are seeing JFET. We will see JFET biasing techniques. So then working of then what is JFET? JFET is a JFET is a three-terminal semiconductor device in which the current conduction is by only one type of carrier, electrons or holes. So here is the diagram. Three terminals are there: drain, source, and gate. Okay, the current conduction is by one type of charge carriers, that is holes. In the n channel JFET, the current conduction is by electrons, and in p channel JFET, the current conduction is by holes. Okay, and the flow of electrons is from source to drain, and the current flow is from drain to source. And in the p channel, the flow of electrons is from drain to source, and current is from source to drain. And then the current conduction is controlled by electric field between gate terminal and conducting channel of device. Here the current conduction is controlled by the gate terminal, which is of p type, and the conducting channel. The box you are seeing, that is the conducting channel. Okay, and the current conduction is controlled by an electric field between this gate terminal and the conducting channel. Okay, drain and source are taken from these two terminals are taken from the n-type silicon bar. Okay, and gate is a p-type material. Okay, and then working of JFET. The working of JFET, and I have missed here one point. It has low noise level. Okay, why it has low noise level means, So low noise, what is low noise application means? A device which has minimum amount of internal electrical noise. So JFET is a low noise application device because they are majority charge carrier devices. Means the current conduction is by majority charge carriers that operate without the high current PN junctions found in BJTs. Okay, and unlike bipolar junction transistor BJTs, which requires a forward bias base current, JFETs use a reverse bias PN junction for the gate. This leads to extremely low input current, which eliminates significant short noise, the dominant noise in the BJTs. So, uh, here in the BJTs, we require a base current, which is due to the electron hole recombination and due to the electrons which are exiting from the base. So, bipolar junction transistors have uh, high noise because of the electron hole recombination. Okay, and JFET, and other reason is JFET conducts current through the bulk semiconductor, means inside the semiconductor material, a channel, rather than along a surface interface, or rather than through oxide interfaces like MOSFET, or forward bias junctions like BJTs. This reduces flicker noise. So in the JFETs, the current conduction is through the bulk of the semiconductor. Here inside the semiconductor, the current conduction is happening. Okay, and not on the interfaces. Okay, and it does not have any oxide, so not on the oxide interfaces like MOSFET. Uh, or forward bias junctions like BJTs. This reduces the flicker noise. Flicker noise means electrical noise in circuits where the noise increases at low frequencies and decreases at frequency as frequency increases. So oxide trap means, so MOSFETs have a conductive channel right under a gate oxide layer, silicon dioxide. So MOSFET have a conductive channel right under a gate oxide layer, silicon dioxide. Here are the two types of MOSFETs. So here, silicon dioxide layer is there. Right under this silicon layer, we have a channel, and here also we have a channel. Here is the silicon dioxide layer. Okay, and then this interface contains some defects traps. Means why it contains defects means due to the gate voltage, applied gate voltage. Okay, if the gate voltage is positive, then it attracts the electrons of the p substrate also in the e MOSFET, and if the gate voltage is negative, then it repels the electrons of the channel away from the channel. Okay, and which increases and decreases the channel size. Okay, and in DMOSFET also it is same. So here we can't we can't decrease the channel, only we create or increase the channel. Here we can increase or decrease the channel by applying various VGS voltages, means gate voltages. Okay, so that's why electrons or holes passing through this channel get trapped or released by these defects. means by gate voltage, so causing fluctuations in carrier number and mobility. These trapped charges randomly turn portions of the channel on and off, creating flicker noise. So that's why it creates a flicker noise. So, and then forward bias junctions in noise in BJTs, the flicker noise generates due to the electron hole recombination, as I said here. Okay. Okay, uh, then we will see the JFET has a low noise because it is a unipolar device. Due to their structure, JFET often exhibit lower internal resistance compared to the alternative transistor and has lower thermal noise. Okay, because the structure is like a box, so it has a so yeah, due to the structure, JFETs often exhibit lower internal resistance compared to alternative resistor and has a low thermal noise. So, due to their structure, so the JFET structure is like this. Okay. So here the JFET structure is like this. Here, here the structure, it has a more area to flow the for the flow of electrons. And JFET often exhibits lower internal resistance, so that's why it exhibits lower internal resistance. So as we observe here in the MOSFETs, in two types of MOSFETs, the so here the channel is very thin. Here also channel is very thin, as means flow of electrons, area of flow of electrons is very thin in these two types of MOSFETs, and here we have a wide area to travel the flow of electrons. That's why the structure, due to this their structure, JFETs often exhibit lower internal resistance compared to alternative transistor and has lower thermal noise. Lower thermal noise means the noise generated by fewer voltage fluctuations caused by the random heat induced movement of charge carriers within component. So means charge carriers are inducing uh, less heat, and that's why the fewer voltage fluctuations are generated. So that's why the lower thermal noise is generated. Okay, and then we will see the working of JFET. In the working of JFET, here the working of in the working of JFET, gate is reverse biased, means negative terminal is connected to the p-type substrate and positive terminal is connected to the n-type substrate, and gate is of p-type material, and S and drain and source are taken from the n-type channel. Okay, and the two p-n junctions act sides at sides forms two depletion layers. Here are the two depletion layers which forms depletion layers, which I have indicated by cross lines. Okay, and the current conduction is by the charge carriers. In this case, free electrons is through conducting channel between two depletion layer and out of the drain. Here the current conduction means flow of current or flow of electrons is between channel and through the conducting channel between two depletion layers. Okay, these are the two depletion layers, and out of the drain the electrons flows from out of the drain in the n channel, and in the p channel the holes flows out of the source. So current will be in the opposite directions. Okay, and the width and hence resistance of a conducting channel is controlled by input voltage VGS. So how means the if reverse voltage is increased, the wider will be the depletion layer, narrower the conducting conducting, hence high resistance. The current from drain to source is decrease. Reverse will happen if VGS decreases. So here the VGS is increasing. So the wider will be this conducting channel. The wider will be the depletion region. Wider will be the depletion region because of the diffusion, as we have already known. So narrower conducting channel, hence high resistance will be there. And means a narrower conducting channel means there is a small area to for the flow of electrons. Okay, so there will be a the current from drain to source is decreases. Reverse will happen if VGS decreases. If VGS is low, then the thin will be the this depletion region, and wider will be the conducting channel, and hence the area to area for flowing of electrons is more, and the current from drain to source is increases. Reverse will so like this reverse will happen. Okay, means the magnitude of drain current, here is the drain current, is changeable by altering VGS. Okay, as we have understand just now. So then we will see the biasing of JFET. So for proper operation of n-channel JFET, gate must be negative with respect to the source, as we have seen in the diagram. And this can be achieved either by inserting a battery in the at the gate, maybe here it is at the gate circuit, or by a circuit known as passing circuit. So what's the actual biasing meaning is, for simplicity and economy, the transistor should have a single source of supply, that one in the output side, VCC. Means JFET can be biased only by using only the drain supply, VDD. Here we require the two voltages. So biasing means by using only the VDD voltage. You will understand this in biasing methods only clearly. Just I am explaining an overview. That is, if so here we are requiring two voltages. So biasing means we require only VDD voltage. Here we apply a VDD voltage, so that biasing is done by it. Okay, biasing means, so here for proper operation of n-channel JFET, gate must be negative with respect to source. This can be achieved either by inserting a battery at the gate circuit, or by a circuit known as passing circuit. So what does it means uh, so we already know gate must be negative with respect to the source, as we have already seen in the working of JFET. This can be achieved either by inserting a battery at the gate circuit, or by a circuit known as biasing circuit. Okay, and then the later method is preferred, because this biasing circuit method is preferred because batteries are costly and require frequent replacement. So means if they fail, they should be replacement, otherwise they will not work. And bias battery, in this method JFET is biased by a bias battery VGG. So I will explain this by using fixed biasing. diagram. So here we are applying VGG voltage, means battery, and here we are applying VDD. Okay, so is by JFET is based by base battery VGG. This battery ensures that the gate is always negative with respect to the source during all parts of the signal. And then basing circuit. The basing circuit uses supply voltage VDD to provide the necessary basing. Means then we have a representation of N-channel JFET, the N-channel JFET and P-channel JFET. So here gate drain source are there and gate drain source are there. The direction is inward for N-channel JFET and the direction is outward for P-channel JFET. So aromatic represents the current flow from P to N. P means P-type material to N-type material. In N-channel JFET, the gate is P-type material, as we have shown in the working, and channel is N-type, and in P-channel JFET the gate is N-type and channel is P-type. So then we will see the different types of voltages that are associated with the JFET, that is VDD. This is the drain supply voltage. Here is the VDD, okay, drain supply voltage, which is connected to the drain. Okay, and the external is the external DC voltage source connected to the circuit. This is the DC external voltage. Okay, this VDS, this is the drain to source voltage, the actual voltage present across the JFET itself. So here is the VDS, drain to source voltage, okay, here is there. And then while VDD is necessary to provide the overall power and push the current, it is VGS that controls the behavior of JFET, like turning it off or on, acting like as an amplifier. So VDD, what it do? It provides the overall power and pushes the current. Okay, and VGS we have already seen in the working, that it controls the whether a transistor should be off or on, acting like an amplifier by widening or narrowing the depletion region. Okay, and then VGG is the gate supply voltage, the external DC voltage source connected to the circuit. In the basing, so why I have shown this in the basing means this voltage is associated with the basing. Okay, basing diagrams, and this VDS is associated with the both JFET working diagram, normal JFET working diagram, and also in the basing diagrams also. Okay, this VDD and VGG is only present in the basing diagrams only. Okay, and VDS, VGS, and other one is VGD, which are present in both diagrams, means in normal JFET diagram and in basing diagram also. And then VGG, this is the gate supply voltage. So here is the it is connected to gate, so it is a gate supply voltage. So, and it is also external DC voltage. Here This is the gate to source voltage VGS and VGG. VGG is a totally removed or set to 0 related to the ground, except in fixed biasing. In all other biasing, we don't have VGG. Okay, VGG voltage. Okay, and where we don't have in in fixed so in the biasing, so where we don't have VGG, we set we totally removed it or set to 0. Okay, so VGS, this is the gate to source voltage. Either here is the gate to source voltage. Okay, VGS. Okay, and that acts as a wall to control the flow of current through the transistor, as we have seen in the working of JFET. And VGD. VGD is the voltage between the gate and drain. This is the gate and drain. Between them, VGD present. Okay. It determines the shape of depletion relay. So, when VGD becomes negative enough to exceed the pinch off voltage, the channel chokes near the drain. Okay. So how it becomes negative enough, and what is the pinch off voltage, and how it chokes the channel near the drain, means choke means the two depletion layer will meet. Okay, we will see now. So this is because the voltage at drain means VD, okay, is high positive, so it accumulates more electrons from the source. So that's why PN junctions at gate and source becomes reverse bias and the depletion layer is increases. So that's why VGD becomes negative enough. So here in the diagram we can see that here is the voltage VD, means drain voltage is high positive. It is high positive. Then so it accumulates more electrons. If I explain here, then we'll understand. So if you apply more high positive voltage at the drain, so it accumulates more electrons from the source. So why it accumulates more electrons from source means the flow of electrons in n channel JFET is from source to drain only. So that's why it accumulates the more electrons. And so the PN junction, here is the N junction. Okay, so the PN junction at gate and source becomes reverse biased and the depletion layer is increased. So yeah, gate and not here source, it is gate and drain. Okay, so PN junctions, these PN junctions will become reverse biased because of diffusion. As I have already said, diffusion means the tendency of electrons of n-type region to diffuse over p-type material, and the tendency of holes of p-type material to diffuse over n-type material. So this is called diffusion. So PN reverse biased occurs, and the depletion layer is increases. This depletion layer increases. Why it increases? Due to diffusion. So here the due to diffusion electrons and hole recombination occurs, and it leaves behind the negative acceptor ions and positive donor ions. As we have already know, p-type materials have negative acceptor ions and holes, and n-type materials have free electrons and positive donor ions. So these negative donor ions and positive negative acceptor ions of p type and positive donor ions of n type is forming the depletion region. Okay, so the depletion region is increased, so near the drain it is increased. Okay, that's why VGD becomes negative enough. So why the VGD becomes negative enough means, here it accumulates more number of electrons na from the source, that's why it becomes more negative. So it exceeds it exceeds pinch off voltage, the channel chokes near the drain. That's the meaning of channel chokes near the drain. So means the two depletion layers meet near the drain. Okay, and then according to the definition of biasing, the VGG is removed or set to 0, so except in the fixed biasing. Okay, relative to the ground. So in other biasing, so here in self biasing, VGG is not there here, it is totally removed, but in the fixed biasing it is there, VGG is there. Okay, totally removed or set to 0 relative to the ground. Okay, and the circuit relies on the biasing techniques to establish this necessary VGS. Okay, except in the fixed biasing. And then, so there are 4 ways of biasing. So fixed biasing, self biasing, voltage divider biasing, and source biasing. And then the required value of VGS, which is used to establish drain current, is obtained from supply voltage in zero signal conditions. Zero signal condition. So required value, we need to find the value of VGS, which is used to establish the drain current, and which is obtained from supply voltage. Here the supply voltage is VDD. I have shown in the diagram earlier. Okay, and then zero signal condition means so zero signal condition means the state where no AC input signal is applied to the amplifier. Okay, but DC supply voltage are connected to keep the transistor active. Okay, and then the value of drain resistance RD is selected to ensure JFET remains in the saturation region. Here is the RD resistor with whose value. So here the value of drain resistance RD is selected to ensure JFET remains in the saturation region. Okay, so why we should carefully select the RD means, if the VDD means the positive voltage is should be sufficient enough to flow the for the flow of current between drain and source. Okay, so that's why we have to select the RD carefully. And then to keep, so here, to keep the JFET operating properly as an amplifier, the drain source voltage VDS must be kept above pinch off voltage VP. So I have already said a pinch off voltage is where the at a point this is the voltage where the depletion and the two depletion layers will meet. Okay, so at pinch off voltage the current become constant, uh, and because the const then so the current is increased to a level and then become constant. uh, so it acts like an amplifier, which is also the increasing the strength of the signal. So then for JFET to remain active, VDS should not fall below VGS minus VP value. Okay, and it should be greater or equal. And there are two types of approaches: mathematical approach and graphical approach. So what are they? We will see in the biasing techniques, and then fixed biasing. Fixed biasing means first we are understanding this diagram. So source is connected directly to the ground. It is here the source is connected to the ground. The negative terminal of the battery connected towards the gate. Here is the negative terminal is connected towards the gate, and the positive terminal towards the ground. Here the positive terminal towards the ground, and then this assures VGS is negative. Okay, so how it becomes negative I will explain in the next upcoming points. So here next, the third point is in zero signal condition, the capacitors C1 and C2 act as a open circuits for DC input, isolating JFET from input signals. Okay, and input signal and load. Okay, so why it is becoming open circuit means for DC current frequency will be 0, as we all know, and XC means capacitance reactance, one that is equals to 1 by 2 pi FC. This is the formula. Then F is 0, we are substituting here, then we will get infinity. And then capacitive reactance, opposition a capacitor offered to the flow of current. Here the current is DC, and hence capacitor blocks the DC and allows only AC. Hence capacitor becomes open circuit. So we are seeing this diagram in case of DC analysis. That's why the capacitor is becoming open circuit. Okay, and then so here we are mainly finding VGG or VGS, or first so in the biasing techniques we are finding VGG or VGS, or and VDD and ID current. Okay, and so the gate source junction is designed to be reverse biased during operation. So we have seen this in the working of construction, means working of JFET. And because the reverse biased PN junction has a very wide depletion region, it offers high resistance input dependence. According to Ohm's law, V is equals to I into R. The voltage drop across a resistor is the product of the current flowing through it and its resistance. Since Ig is effectively 0, see Rg is equals to 0. This becomes 0. Okay, Ig is 0 because of reverse biasing. Okay, that's why Rg is also 0 according to the Ohm's law. Because there is no drop, the resistor Rg acts like a simple wire for DC analysis. So it acts like a simple wire. Okay, ensuring the full potential of the battery reaches the gate. This battery's full potential is reaching the gate. Okay, and then VGS. VGS determines VGS determines the path. VGS determines how much current ID flows through the drain. Okay, if we follow the path from the ground through the VGG source, here is the one. Here is the one from the ground through the VGG source through RG voltage to the gate and back to the grounded source. Here is the source. So the source is at 0 volt, and battery VGG is connected with its negative terminal, as we can see here. And since there is no voltage drop across RG, the gate terminal sits exactly at the potential of the battery's negative terminal. So to understand this statement, we have to understand what is voltage drop. So if we think of a voltage as a water pressure and current as the flow of current, flow of water, if we think of a voltage as a water pressure, okay, and current as the flow of water, and a resistor is like a narrower pipe. As water flows through the narrow pipe, pressure is lost due to friction. In electricity, as electrons flow through a resistor, they collide with atoms, converting some of their electrical energy into heat. Okay, a voltage drop represents the work done by the electrical charge as it passes through a component. So as we all know, Ig is equals to 0. If there is no current flow, there is no energy being spent, and thus 0 voltage drop occurs. Near the RG resistance. Okay. So then we will understand this point. Since there is no voltage drop across RG, the gate terminal sits exactly at the potential of the battery's negative terminal. Here we have no voltage drop. So the VGS, here is the VGS, okay. Here is the VDS. And here is the gate, here drain, and here source. Okay. So this VGS voltage sits exactly the potential of the VGG, because there is no potential drop at the resistor RG. Okay. And then, so voltage at the gate relative to the source is VGS is equals to VG minus VS, that is equals to minus VGG minus 0, that is equals to minus VGG. Okay, VG we have taken minus VGG because VGG is a minus negative voltage. Okay, and VS we have already know 0. Okay, that's why we got minus VGG. And then then mathematical approach and graphical approach. So before that, so under zero signal condition, ID is controlled by fixed VGS. Okay, so name is fixed biasing. And then mathematical approach and graphical approach. So here is the mathematical approach of fixed biasing. So here we are Mathematical approach means applying KVL at input and output sides. Okay, then if we apply voltage at input side, here is the diagram. Here is the VGG. It is VGG. Okay, so input side means this is the input area. Okay, and this is the output area. Okay, so by applying KVL, we got VGG. Here is the VGG voltage. We have supplied here VGG voltage. Okay, and then VGS. Then VGS minus VGS minus IG into RG. So IG is here 0. So the whole term becomes 0. That is equals to 0. And VGG is equals to VGS. So next, applying KVL to output side. So this we have achieved theoretically also, and then applying KVL on output side. So here is this is the output side, this is the input side. So VDD minus IDRD minus VDS. Okay, that I have written here. Then VDD is equals to IDRD plus VDS. That is ID is equals to, so ID is equals to VDD minus VDS by RD. So we got ID is equals to VDD by RD minus VDS by RD. And then graphical approach. So we use this formula. So to check how the VGS is varying and how the ID is varying. So if VGS is 0, then ID is equals to IDSS, means maximum. Okay, maximum current. VGS is VP, ID is equals to 0. If we substitute VGS is equals to 0 here, the whole, so here if VGS is equals to 0, 0 by VP, 0 by something, that is equals to 0 only. So we get IDSS only. So ID is equals to IDSS. And if VGS is equals to VP, VP cancelled, and 1 minus 1 0, and IDSS into 0, that is equals to ID is equals to 0 due to combination of two depletion layers. Okay, at a pinch of voltage, this will be the graph. VGS is equals to VGS. ID is increasing linearly with the VGS. Okay, and then self-biasing. We have a self-biasing. So here, self-biasing, the resistor RS is the biasing resistor. So which means that provides the biasing. Okay, here is the RS resistor. Okay, so the DC component of drain current flowing through RS produces the desired voltage. Here the DC component flowing through the RS resistor produces the desired voltage. Okay, so voltage across RS, Vs is equals to ID into RS. Okay, because we already know Is is equals to ID. So actually it should be Vs should be Is into RS. We are replacing Is with ID. That's why we got Vs is equals to ID into RS. Since the gate current is negligible, small, because we have seen the PN junctions are reverse biased. Sorry. Whoa. The gate to source voltage is reverse biased. That's why the IG current is small. The gate terminal is at DC ground. Okay, here is the DC ground, and VG is equals to 0. As IG is equals to 0, then VG also 0 according to the Ohm's law. And VGS is equals to VG minus VS, that is equals to 0 minus ID into RS. We are substituting this previous value in VS value. and then VGS is equals to minus IDRS. So that's why bias voltage VGS keeps negative. Bias voltage VGS keeps gate negative with respect to the source. Here is the diagram. Here is the diagram. The DC analysis explanation, which is why the capacitors are becoming open, is same for this diagram also, means self biasing diagram also, and for all biasing diagrams, this capacitor opening explanation is same. Okay, and then I have removed and redrawn this diagram. So, and then here the gate is held at 0 ground. Okay, gate is held at 0. Okay, ground potential. Source terminal sits at a positive voltage. This source terminal sits source voltage sits at a positive voltage, means ID into RS. Okay, the gate to source voltage becomes negative, which controls or biases the transistor. Okay, so this becomes VGS becomes negative. This statement I have explained here. VGS is equals to VG minus VS, that is equals to 0. That is equals to 0 minus VS. Okay, that is equals to minus IDRS. We are substituting previous VS value. Okay, and then the ID current flows from VDD, voltage from VDD through RD resistor, and enter the drain and passes through the channel, exits through source resistor RS and to the ground, and then applying KVL at input side. So here we have applied KVL at input side. So here is the diagram. Don't consider this line. Okay, these are connected to ground only, these both resistors. This capacitor will not be there. Okay, this is also not there. Okay, and then at input side we are applying it. Okay, KVL. So VGS. So since there is no VGG battery, so we are directly taking VGS. Okay, VGS, then IS into RS. IS into RS, because IG is 0, so RG is also 0. This IG into RG will become 0. So we are not considering that, and then we are taking IS into RS, and then VGS is equals to minus ID into RS. So we are replacing IS with ID. Okay, we get this, and then this equation we have seen theoretically also, and ID into RS is equals to minus VGS, rearranging it, and then further rearranging, we got the ID is equals to minus 1 by RS into VGS. So it is in the form of I is equals to minus mx plus 0, and then applying KVL on output side. So VDD minus IDRD minus VDS minus IS RS is equals to 0. So here is the VDD and then minus RD into IS minus VDS, then ISRS minus ISRS is equals to 0. So we have already know IS is equals to ID, then VDD minus ID into, here we are replacing IS with ID. So we are taking RD and RS common. Minus VDS is equals to 0. For we got the equation for VDD is equals to ID of RD plus RS plus VDS. Okay, and then so by applying KVL we got the VGS value, and by applying KVL on output side we got the VDD and ID value. At input side we got VGS. Okay, and then graphical approach is same. Graphical approach is the graphical approach for four types of biasings uh, are having same calculation, that is VGS is equals to 0, ID is IDSS, and VGS is equals to VP, the ID is equals to 0, and the graph will change. Okay, the graph is IDSS VGSS. So here the line is minus 1 by RGS. So here slope M we got minus 1 by RG, and VGS is X. Okay, so the line is minus 1 by RGS. So till now we have completed up to self biasing. So that's it for today's class. If you have any doubt, ask me in the comment section. Um, if you feel this video is helpful, then subscribe, like, share and comment, and thank you. Bye.